I would like to first point to two general principles the brain may utilize to get this kind of robustness, flexibility, and autonomy, which we really admire as living beings. And in the following two steps, I will try to show how we try to implement that principle into our systems and what we gain from that. So clearly, our technical artifacts are typically optimized for pre-specified working range. However, if the systems have to operate in complex non-stationary environments, they need to rapidly adapt to non-fluctuations of constraints for the operations, a capability which we call intelligent behavior, and clearly the need for this kind of intelligence becomes particularly visible when dealing with human robots. And as I said, brains achieve this autonomous adaptation to a changing world still unparalleled by any technical system. So the idea is, I think, reasonable that we should look at the brain for getting some inspirations. We actually started with that strategy 30 years ago in our institute at Offenbach, but rapidly understood that there is nothing like ready for use concept or that alone principle from brain science or computational neuroscience or cognitive science you really can utilize, but that we have to think by ourselves. And I think this is still a problem in this new hype of brain-like systems, that there is a missing gap between the biological phenomena which we can observe and the technical system for which we would like to show the same performance. So this kind of modeling and extended modeling, not only of the observed phenomena, but the principles behind which we could then utilize as technicians. That is still the point of, I think, research challenge, which is, for my understanding, not yet well addressed. But anyway, at the level of behavior, where we really can try to say, make kind of proof of the plausibility of our ideas, we can try to find some inspirations. And the one concerning learning, I would like to point out now. What our technical artifacts are doing already quite well is solving well-defined static problems. What we would like to have is clearly the same characteristic like living beings being able to cope with the constraints of a very wide problem space. And the problem is that for a kind of well-defined static problem, we can predict any configuration, so we can actually pre-program anything. We can make a rule base. This is not possible for such a situation like this traffic scene. And therefore, what we have to do is to try to learn in interaction with the environment to have the knowledge ready for solving these problems. For that purpose, and the talk at the beginning, our distinguished colleague was dealing already also with that kind of technology. We have already a very efficient learning technology, statistical learning technology, which is successful in computational intelligence and surely also in the living being. However, this kind of statistical learning has some drawbacks that we need large number of samples. Usually we learn offline, and we learn complete data sets. That's not an incremental learning. So it's just another kind of pre-programming, and it doesn't solve the problem we want to address. What we need is really incremental learning. Incremental learning in the way of learning during behavior. Online, from our experience, we have the need to learn from few samples, or even one. So if there's a dangerous situation, we shouldn't need maybe 20 or 50 or even 10,000 times the repetition of this dangerous situation. Let alone that we cannot try to repeat complex situations again and again and again. And what we need is to have a more efficient learning regime, like learning by imitation, what is observed, and learning by active exploration. So this is a kind of required learning regime, a learning control, which would solve our problem. However, we need a dynamic control architecture for solving the three essential questions. So, what should I learn? Is this sufficiently important or relevant that I learn that? And if I have to learn that, how should I integrate this new knowledge in this already acquired knowledge in order to keep a kind of consistent relational architecture? So, the control of learning is one of the key aspects, but it's not only the control of how to acquire knowledge on the environment. The next problem is we have also to understand that we have to learn how to program the system itself in order to get the right information from the environment at the necessary moment. So coming back to our initial image, so this is what we can realize today, our technical artifacts with good performance for a limited set of constraints and problem space. And what we would like to have is this wider performance characteristics of the living being, like but if we think it through, we may have to find a more robust kind of architecture, but really any algorithm has a limit in its robustness and at the same time good performance. So we may end up and trying to create a number of different architectures which we can combine in a way that for a certain situation we simply use a different architecture. And that means we create a kind of robustness and flexibility by programming on the fly, simply dynamically changing the processing architecture based on the required behavior or based on the changing situation outside. So, and we try to do that and prove that concept by top-down selection and parameterizing of required modules for optimally solving a task, and the bottom-up driven adaptation of the modules for optimal tuning to the input signal statistics. And that I will try to show you for the case of a cognitive vision system. So if we have the job of trying to understand a traffic situation, then clearly there are a lot of visual processes necessary which enable us to make a kind of scene analysis and scene understanding. So visual routines like scene gist detection, engagement tracking, disengagement, saccades, and so on, echo-motion compensation. And what this is about is that we clearly cannot use the traditional vision process, which is sensory data driven and after a parallel filtering stage simply categorizes them as a result. But what we need is to have a system which is driven by behavioral needs and which is actually a kind of bottom-up and top-down confirmation of hypotheses generated by simply selecting a behavior. And if you select a behavior in such a system, it automatically gives a hypothesis of what should be outside, what should be in the scene, if this behavior should be realized successfully. So there is a top-down propagation of expectation, which is shaping the system in a way that the necessary modules are activated and parameterized, and which then is trying to find in the input stream of sensory signals relevant aspects which could be related to the sought after concepts. So the essential point here is that in between this, in between this higher level scene representation and understanding part, sending the hypothesis or developing the hypothesis, and the real world signal input, we have a kind of adaptive interface established by these visual routines, where we have a kind of low-level routines which simply adapt to the input signal statistics to show the system the environment more regular than it is actually. We have more strongly top-down controlled visual routines like tracker, which is really initiated to search for something, or even object-specific visual routines, which are then trying to localize a certain object. And the essential point is here, while the filtering and classification of sensory data is definitely not a perception, the confirmation or even non-confirmation of a hypothesis is a kind of such perception. And the essential point here is that we have elastic coupling of this abstract concepts to the fluctuating sensory input signals, which gives us a very robust behavior of this system by this steerable visual routines. So at the upper part, the scene understanding part, we have a dynamic model of scene plus the word knowledge, which consists of typical contexts, predictions, causes, and really also includes ontology of representations, which combines both the provided and the acquired knowledge. And at the level of steerable visual routines, we have routines like routine to fixate, routine to track, a KIST routine, for instance, or this compensation of ego motion and much more. These routines have a lot of adaptability included. For instance, the tracker here already has the capability to predict a changing of shape if a certain object is either rotating or moving to or from the observer or have a translation. So this prediction enables that the tracker can keep the object even if the object is changing its shape and appearance. The first part of the story is that in between of these steerable visual routines, we have a kind of complementary processing. That means mutually supporting processing pathways, which essentially means that the uncertainty of processing in one channel is compensated or improved by the processing result in a complementary channel. One example of that is, for instance, the combination of depth and motion. So the typical state-of-art fusion for motion and depth is shown here. But if we look a little bit more close to the biological system, then we find that we have feedback, which is not only going to the same channel back, but also to the complementary channel. And this is not a feedback of the typical signal type of feedback to the source of the lower processing steps, but it's actually a control feedback which tunes the parameter in the complementary pathway to optimize it for the current situation in order to improve processing. And what you see in the videos, so at the left-hand side, that's a typical traditional processing of the Q fusion. while at the right-hand side you see the improvement by this complementary processing. And you see that this is definitely much better to use for the purpose we need. And now the next step is this programming on the fly, the knowledge-based control of processing. So if we establish a kind of hypothesis here, either by the gist of the sensory input or by the intention to trigger a certain behavior, then this upper level system establishes expectation, and this expectation assembles a number of those channels and parameterizes these channels. I will show a video which shows the tracking of different objects like cars and bikes in different situations. So for instance, with strong contrast changes here, very hard shadows, very difficult for the vision processing, or night with a lot of irritating lights and reflections, rain with vibrant reflections and white on white problems, and several simultaneous objects. And you see that the tracking is very stable. And I have to say that this is also true for the recognition of the objects in different situations. So this system has a performance over 90% for the best situation, daylight, and in different difficult situations like as shown here, the performance drops around to 90%, while competitive current approaches have a performance for the daylight about up to 90%, and in other conditions the drop is down to 60% or lower. So this is the main aspect of this programming on the fly. So for me, a nice side effect is that this is a kind of smooth signal-to-symbol transition by relating this high-level abstract and behavior-related concepts to signal-level patches of pixels in a very reliable and also a robust manner, simply by this kind of top-down programming and parameterizing the adaptive interface. Now to some comments on learning semantics during interaction and learning from imitation. So when we want to implement a learning control for a humanoid robot, we actually have to implement almost a complete control architecture, because this means the robot has to search for some object or some candidate of object, which we call a proto object. Then the robot has to fixate and to track, and then to approach this object, to discriminate the object. And if the robot has stabilized the object, which maybe is not yet known, then the learning can start. And so I have shown at the left-hand side a very coarse characteristic of certain typical large-scale areas of our brain. This is a related functionality which I have written down here in the abstracted cognitive architecture. And the right-hand side, you see actually the systems instance, what we actually implemented. The important aspect here is that we used a nested hierarchy control where we have at the bottom a lot of reflex-like loops which enable and ensure all the necessary processes to keep the system in a working range, including collision avoidance, and then step by step the other functionalities are added, and every next higher level has the ability to take control, to take control from the respective lower level, as long as the lower levels, the optimal range is guaranteed. If the lower level optimal range is left, for instance, coming close to a dangerous situation for collision, then the lower level takes back the control, and the higher level has to grant the control back until this problem is resolved. So by this characteristic, we get a robustness by fallback option to lower level behavior, and don't get into the problem of getting stuck in any situation. And here a video which we made 2 years ago.
Normally, speech recognition is done using some sort of microphone.
The screen recognition is done through ultraviolet ears. Noise we hear is generated by osmosis fans and motors.
So now we tried to learn representations which the robot needs to understand commands and interact with the person, like what is left, what is right, what is bottom, what is up, what is large, what is small, and so on. And we integrated audio representation with these different concepts.
Bottom. Okay.
Now the robot learns the concept large, and you see large was already
large. Take.
And here the robot should take. It looks like he's thinking over, but actually it's only the internal simulation running in parallel several alternative behaviors and selecting the best one. So depending on the relative position, it selects the grasp with right or left hand.
Release.
Another stroke of work is to acquire skills through learning. Here the target is to learn movement motifs for skill learning, and later to combine imitation learning and exploration. So in this first step, we had a two-step generalization ability. The first generation was according to the measuring of the variance of the observed movements. So our intention was not to imitate the trajectory, but actually that the robot understands the purpose of movement. That means where the variance is lowest, the robot has to comply as close as possible with the observed movement. But if there is part of the movement which was observed with high variance, that gives the robot the freedom to modulate the behavior in order to, for instance, avoid obstacles. And the second aspect of generalization over various options to achieve the task is based on the movement representation in body schema, which enables the generation of action by various body configurations, so that even if the robot learns one movement only with the left hand, it automatically can also perform it with right hand or with both hands. And you see the performance here. So it's working with the internal simulation. That's the internal image of the robot about the theory. The student here demonstrate what should be done. And if a student raises the left hand, means learn that. If a student raises the right hand, please repeat it. So the recognition is quite simple, based on color and letters.
Okay, I'm learning what you showed me.
You see here this arrow. So it's an object which is demonstrator touches first or shows with or points with the finger is the one which should be moved, and the attention is then moved to that object.
Okay.
So really the demonstrator should show this movement in not only one way, but in different possible ways in order to explore this kind of robustness by observed variability. Now the tutor points to that object, that means the robot should take the red one and put it on top of the green one. Here you see also a problem which we still have to solve. The tutor showed the movement with the right hand, but the robot simply used the same side, left hand. So it's not yet the reflection to putting himself or itself in the shoes of the demonstrator. And as I said, by this specific representation in body coordinates, the robot can now also, without being taught to do so, use both hands in order to perform this task. Okay. Yeah, as a short summary and outlook, I think it's, as I said in the beginning, probably an important step in also understanding the brain better than before, that we now have a means, a tool, to really verify large-scale computational hypergroups in the function of the brain. And I think this is definitely one of the important aspects we also have to care for with our development of humanoid robots. Then the capability of segmenting and preserving behavioral relevant situations for learning from few experiences, or even only one, defines the degree of intelligent behavior a system can develop. I think you will agree, and that means the control necessary, and also the internal processes we have to include in our systems to make this possible will simply define the progress we can reach here. And finally, I think what we should think about is that we should stop building dedicated systems for each cognitive capability, but we should explore how to build dynamic systems that can rapidly configure themselves under control of static information previously acquired, and then allow sensors to hand over control to changing sensory signals. That's what I wanted to give as a message here. It's not only that we have to learn objects and situations of our outside world, but also how to organize the internal processing architecture in a way to best respond and interact with the current sensory situation. Thank you very much.